In this video, we will look at planes in Mobius. Conceptually, a plane is an infinite flat surface. The plane has an origin and a set of local axes that give the plane a particular orientation. The plane's surface is defined by the local xy plane. So the local z-axis is perpendicular to the plane. As with rays, planes in Mobius are mathematical constructs. There are no geometric entities for planes. A plane is represented using three lists of numbers. The first list is the origin. The second list is the normalized x-axis vector. The third list is the normalized y vector. The y vector must be perpendicular to the x vector. A series of 6 plane constants are provided. These define default planes. XY plane is the same as the global coordinate system. The other 5 planes all differ in orientation from the global coordinate system. For example, the YZ plane is rotated, so that the local z-axis is aligned with the global x-axis. Other planes can be defined that are translated and rotated relative to the global coordinate system. All these types of plane can be used to define a local coordinate system. Various functions can accept planes as inputs. For example, the functions that generate patterns of positions can use the plane as a local coordinate system. Let's have a look at some of the functions for working with planes. First, we will look at the sum of the primary functions. After that, at the inline functions. The calculate.plane function can be used to create a plane from polygons. The function is overloaded. If you provide a list of polygons, it will return a list of planes. The plane origin will be positioned at the centroid of the face. The x-axis will be aligned parallel to the first edge of the face, and the y-axis will be aligned perpendicular to the x-axis. The modify.mirror function can be used to mirror entities in a plane. In the example, you can see a box being mirrored in the plane. Note that mirroring polygons will reverse their direction, so you need to add a modify.reverse function to flip them back again. The modify.rotate function can be used to rotate entities around a ray. However, you can also give the function a plane, and it will create a ray from the plane z-axis. In the example, you can see a box being rotated around the z-axis of the plane. Many of the functions that generate patterns of positions accept planes for their origin parameter. If you specify just a set of xyz coordinates, then the function will generate a default plane with the origin at that location. The axes of the default plane will be aligned with the axes of the global coordinate system. If you don't want the default orientation, you can also specify a different plane. The positions will then get generated relative to the local coordinate system defined by that plane. Let's look at an example, the pattern.rectangle function. Here is the result of calling pattern.rectangle function with the origin set to xy plane constant. The default plane will be used, aligned with the global coordinate system. Here is the result for all of the plane constants. For clarity, the back of the polygon is shaded red, and the front white. You can see that the choice of plane constant affects the direction in which the polygon is facing. Here is the result of calling pattern.rectangle function, specifying the xyz coordinates of the origin. A plane will be created, with the origin at the specified location, and with the axes aligned with the global coordinate system. And here is the result of calling pattern.rectangle function specifying a non-standard plane. The positions will be generated on the surface of the plane. Often when you work with plane, you do not generate the planes from scratch. Instead you get planes from existing geometric entities. In this example, a series of polygons are created in an arc form. A list of planes is then generated from the polygons using the calculate.plane function. A grid of positions is then generated on each plane. You can see that each grid has been generated relative to the local coordinate system defined by the plane. We can have a closer look at the pattern.grid function to see how this works. The pattern.grid function has a number of parameters. The first parameter is the origin, which is overloaded to also accept planes. The second parameter specifies the grid size. The third parameter specifies the number of positions. For grid size and number of positions, you can specify one number or a list of two numbers. If you specify just one number, the same value will be applied in x and y directions. If you specify a list of two numbers, then the first is applied in the x direction, and the second in the y direction. The x and y directions that are used will be relative to the plane's local coordinate system. As a result, the grid is always orientated in the same way. Next, let's look at the inline functions. A set of inline functions are provided for working with planes. The first function is the plane make function. This function will create a plane from an origin and two vectors. The function will make sure that the vectors are orthogonal and normalize them so that they have a unit length. The first vector is assumed to be the x-axis. The second vector is assumed to be any other vector in the xy plane. The function will then calculate the y vector that is orthogonal to the x vector. The plane move function and the plane rotate function can be used to move and rotate planes. With these functions, the planes are moved and rotated relative to the global coordinate system. Here we can see a plane being moved 5 units in the z direction relative to the global coordinate system. The plane can also be moved relative to the local coordinate system. Here, we can see the plane being moved 5 units in the z direction. But this time it is relative to the local coordinate system of the plane. This uses the plane local move function. The same applies to the rotation. Except that for rotation, 3 separate functions are provided, for rotating around the 3 axes. For example, the plane local rotate x function rotates around the x-axis of the local coordinate system defined by the plane. Next, let's have a look at how we can visualize a plane. Since planes are not geometric entities, they are not visible in the Mobius viewer. So when you create a plane, you will not see anything in the viewer. This is similar to rays. However, sometimes it is useful to be able to see planes. It can help to better understand what is happening and to verify that the planes are actually in the correct location and orientation. The visualize.plane function can be used. The function will generate some polylines. The square polyline represents the xy plane.
The 3 other lines represent the x, y and z axes.
By default, the lines are 1 unit long. The second argument of the visualize.plane function is a scale factor, which can be used to increase the size. This can make the plane easier to see. As with rays, note that the lines generated by the visualize.plane function are just polylines. The polylines that it generates cannot be used as arguments to functions that are expecting a plane. Lastly, the visualize.plane function is overloaded. If you pass in a list of planes, it will visualize all the planes.